Okay, so thank you for the great introduction, Dr. Kathuria. Yeah, so hello all. So first of all, thanks for giving me this opportunity to share some words while sitting on the other side of the screen. I have spent most of my time, as most of my college life, while listening to similar tech talks and short trainings by the brightest minds like the ones who already presented and the ones who are yet to. I really feel humbled. Yeah. So the topic for today's talk would be anomaly detection. We'll be looking into the various algorithms which complement this concept, the different use cases, and definitely have some quality hands-on at the end of the session. So a little about me. I'm Nikhil, originally from Delhi, and currently I've been living in Germany for the past 3 years. In my current role, I'm working as a data scientist, like Kathuyam already explained. I'm working with a company called Check24, which is a comparison portal and performs price comparison for different verticals like hotels, insurances, and so on. Here I am generally working with the different types of recommender systems which generate product recommendations for users on our website and also for the newsletters. Other use cases include email classifications, doing price forecasting for hotels, categorizing hotel images to be belonging to one of the many categories. Previously, I was also working as a part-time data science researcher at Fraunhofer, which is Europe's largest application-oriented research institution. There, I was responsible for development and validation of data-driven monitoring systems for the smart factories. This is the place where I came across the topic of anomaly detection. Um, In parallel, I also did my Master of Science from the University of Paderborn here in Germany, where I specialized in signal, image, and speech processing. And my master thesis was based on using deep learning for anomaly detection in autonomous systems, which was also quite successful work, which we'll be talking about also in this session. And back in India, I did my bachelor's from Guru Gobind Singh Interpurse University in electronics and communication engineering, and worked there as a software developer for around 3 years before coming to Germany. Enough about me. So let's see what the outline for today's session. We will start with the introduction and understand the motivation behind this talk and discuss about the concept of anomaly detection in brief. Further, we'll differentiate between an anomaly, an outlier, and what is a noise. Next, we'll be looking into the causes behind the anomalies and understand the underlying key components and challenges that we face while doing this task. Later in the talk, we discuss in detail what are the aspects that differentiate between the different type of anomaly detection problems. This is a topic, this anomaly detection is a topic which is applied in various areas, which will be covered in the application section. Now, a single anomaly detection algorithm cannot be used for every problem, and that's why we need to understand what are different techniques available at our disposal. So like classification-based techniques and nearest neighbor-based techniques. And lastly, we discuss in detail a real-life use case I also worked on in Fraunhofer and see the results for the different anomaly detection techniques used there. And if time permits, I will also demonstrate a tutorial where we get to see how the concepts we will talk about come together in one place and to solve a problem. It depends like how much time that we are left. We'll do it in more detail, or we can quickly skim through a Jupyter notebook that I have prepared for this session. So yeah, let's get started. Digital transformation, digitalization, Industry 4.0, predictive analytics, and so on. These are all the terms you have probably heard or read about before. However, all of these buzzwords, the main goal is the use of technology and data to increase the productivity and efficiency. The connectivity between the different devices and sensors, it allows us to an abundance of data which is available at our disposal. And now the key enabler is then being able to use this vast information and actually extract something useful out of it, making it possible to reduce the operational costs, like optimizing the capacities and keeping the downtime to a minimum. This is where the machine learning and data analytics will come into play. So let's define anomaly detection. So anomaly detection is identification of rare items or events or observations which raise suspicion by differing significantly from the majority of dataset. So for example, the one we see in the figure, this is kind of a time series graph, and the one which is marked as anomaly is the one which is the value is significantly different from the average value of the time series. So typically anomalous data can be connected to some kind of problem or rare event such as bank fraud, medical problems, malfunctioning equipment, etc. This connection makes it very interesting to be able to pick out which data points can be considered as anomalous, as identifying these events or observations are typically very interesting from a business perspective. It also finds an importance in a wide variety of application domains due to the fact that anomalies in data, they translate to a very significant and critical and actionable information. Based on the application domain, these non-conforming patterns, they might be referred to as anomalies, outliers, exceptions, peculiarities, contaminants, and so many other names. But the ones which are common, which are very popular, are the anomalies and outliers. Let's see how we can differentiate between these two. So basically what are outliers? So outliers are patterns in the data that will not conform to a well-defined notion of normal behavior. So like outliers and anomalies are often used interchangeably, but most of the important characteristic of anomaly is the fact that it is interesting to the analyst for the reason that it carries some significant information and some actionable information. So at the end, it will be analyst decision when to classify an outlier as an anomaly or it will be just some random outlier. So in the figure, we can see the distribution of a simple two-dimensional data set. The data, it has two normal regions, N1 and N2. Since most of the observation lie in these two regions, points that are sufficiently far away from this two N1 and N2 region, for example, like the O1, O2, and the points in the region O3, they might be classified as anomaly. There's another thing called noise, which can be defined as a phenomenon where the data is not of interest to the analyst, but it basically acts as a hindrance to the data analyst processes that we are performing on the dataset. So we need to remove these unwanted objects, these noise, before any data analysis can be performed on the dataset. Just for the record, if you have any questions, please just note down the slide number and then we can come back to at the end of the session for this, for all the questions. Yeah, now causes of anomalies. So anomalies occur due to a number of reasons. Oftentimes, they are just samples which belong to a different generating process, which are either not known or were not present in the training data. But it is also possible that they might be just another unexpected class carrying significant information and their detection is of utmost importance. For example, knowing when a cancer development might be malignant or when it is benign, or defining when a suspicious bank transaction is valid versus when it is fraud, and so on. However, at times it is also possible that these observations just happen to naturally lying just because of the naturally lying in the less frequently seen category. Like in the Gaussian distribution, the samples which lie far from the mean, 3 standard deviations away from the mean value, they can be considered an anomaly at certain times. And lastly, it is very much possible that the suspicious looking instances, they are just a result of a genuine human error or something going wrong with the measurement devices, and which also happens quite often and depends on the use case. These might be interesting to the analyst or might not be. Challenges. So in principle, a straightforward anomaly detection approach should be to define a region representing normal behavior and declaring any observation in the data which does not belong to this normal region as an anomaly. But several factors make this simple approach very challenging. We will be seeing those in this slide. So defining a normal region which includes every possible normal behavior is very difficult. Also, the boundary between the normal and anomalous behavior is oftentimes not very precise. And that is why it is possible that an anomalous observation which is lying close to the boundary can actually be normal. And it is also possible vice versa. The second is the exact notion of anomaly is different for different application domains. For example, in the medical domain, a small deviation from the normal, example, the fluctuations in the body temperature, they might be an anomaly. However, a similar deviation in the stock market domain might be considered as just normal. Thus applying a simple technique or a technique which was useful in medical domain might not be so useful if we apply it directly to the stock domain. So a direct replacement for the technique from one domain to another is oftentimes very challenging. The other reason is that in many domains, definition of normal behavior keeps evolving, and the current notion of normal behavior might not be so correct in the future. So this definition of normals, it is changing over time. And that's why we need to keep the models updated, and we cannot just rely on the simple rule-based systems. At most of the times, this availability of the labeled data for training and validation of our models used by the anomaly detection techniques is a major issue. It is most of the times it is not available. So most of the data that we generally collect, they are without any labels. And doing labeling manually is very expensive and very it's not very cost efficient. Lastly, the data sometimes contain noise, which tend to be similar to actual anomalies and hence is difficult to distinguish and remove. All these challenges, they make the task of anomaly detection not really easy to solve, and which we'll be seeing how we can do so in the coming slides. Key components. So from a broad point of view, these can be identified as the key components of the complete anomaly detection problem. The concept itself belongs to a number of most active research areas like machine learning, data mining, or spectral theory, and so on. As mentioned before, and it will be also discussed later in detail, the anomaly detection problem is found in a number of application domains ranging from a minor fault detection in a factory machine to advanced healthcare systems. Lastly, a formulation of the problem is determined by several different factors such as the nature of the input data, the availability or the unavailability of labels, as well as the constraints and requirements induced by the application domain, and which we'll be looking into the last problem, the last component, which is the problem characteristics. We'll be looking more into detail in the coming slide. So this is these four components, these four key aspects representing any anomaly detection problems are the nature of input data. It can be further divided into attributes, sequential data, spatial data, and so on. Or it can be, and there's like the type of anomaly, the output of the anomaly detector model, and the availability of labels. In the upcoming slides, we discuss each of these in further detail and justify the need for the broad spectrum of anomaly detection techniques which is required for our problems. Yeah, maybe take some time to look at the different classifications or the different hierarchies. Yeah, so first point is nature of the input data. The input data that we generally have is a collection of data instances, and each data instance can be described using a set of attributes. These attributes can be different types, like it can be binary, categorical, or continuous. The binary attributes, we all know, can only have two valid values like 1 or 0, male or female, yes or no. Like in this data set that is present on the slide, we have the gender, basically like male or female. It's a binary value. It's a binary attribute. The continuous type generally have a real numerical value like the price of a product, profit made by a business, and so on. Like in this case, it's the profit, right? And then we have the categorical value, which is generally used to name the variables without providing any numerical values or numerical input in that variable. So, for example, the name of the people, name of the person, or of this race, which is in the in this data set. And another classification can also be made based on the number of variables which are present in the data set, or the ones that we are using for the analysis at least. For example, the first can be univariate, which basically contains only one variable. So the analysis of univariate data is like that's the simplest form of analysis, since the information we are dealing with is only one quantity that is changing. It does not deal with any kind of relationship between multiple variables, and thus the main purpose of the analysis is to describe the data and find patterns that exist within it. The next one is that we have is bivariate. So bivariate data involves two different variables, and the analysis includes the relationship between the two variables. Similarly, the multivariate, it is similar to bivariate, but only that we need more than three variables, at least three or more variables. But yeah, all these variables are dependent on one another, And depending on the analysis, we can classify our data set to be belonging to one of these categories. Another important aspect is of the anomaly detection technique is the nature of desired anomaly. Um, if yeah, so like we can see in this, this is the same figure that we used previously in the previous slides. So if an individual data instance, it can be considered an anomalous, it can be considered as an anomaly with respect to the rest of the data, then the instance is termed as a point anomaly. So like if we can identify or pinpoint to one single data instance which is deviating very far from the normal data range, then it can be considered as a point anomaly. In this case, this is the simplest type of anomaly, and it's the focus of majority of the research problems on anomaly detection. For example, the points O1 and O2 and all the points in the region O3 in this case will be point anomalies. A real life scenario would be like consider a credit card fraud detection. The data set would be the individual's credit card transaction. So a transaction where the amount spent is very high compared to the normal range of expenditure for that person will be a point anomaly. It is possible that someone else has got the access to his or her credit card and did this kind of fraud. So that is an example of point anomaly. The other type we have is contextual or conditional anomalies. So if a data instance is anomalous in a specific context, but it is not otherwise, then it is termed as a contextual anomaly or a conditional anomaly. So the notion of the context is understood by the structure in the dataset, and it has to be specified as a part of the problem formulation itself. So for example, the longitude and latitude of a location, we can define, so then we have a data set where the longitude and latitude, they might be defining, okay, what kind of context we are talking about. So like, are we talking about India? Are we talking about Germany? Are we talking about America? So this longitude and latitude will provide this kind of context. So generally every data instance, it will be having two different set of attributes. In this case, in the case of contextual anomalies, we have contextual attributes and behavioral attributes. The contextual one, like already mentioned, like the longitude and latitude. And if we are trying to measure like what was the amount of rainfall which happened in a particular area, then the longitude and latitude will give the behavioral will give the contextual attribute, and the amount of rainfall in millimeters or centimeters, it will give us the basically the behavioral attribute, which are basically not the which are basically complementing the previous attribute with some more information on top of it. We have a figure on the right, which basically is a temperature time series. It has recorded the monthly temperature for an area, for certain area over last few years. As we can see, a low temperature might be very normal when we are talking about winters like December, but the same value, if it is occurring during summers, it would be an anomaly. So in the figure, we can see like the same temperature at T1 and T2 in December and in June, they are the same value. But it's the context, like first T1 is happening during the December, while the T2 is happening during the June. And the ones during the T2 will be an anomaly. And lastly, we have this collective anomaly, concept of collective anomaly. So it is an anomaly which like where the collection of related data instances, they will be anomalous with respect to the entire data set. We are talking about a collection here. So the individual data instance is in a the individual data instance in a collective anomaly, they might not be anomalous by themselves, but their occurrence together as a collection will be anomalous. So for example, this figure here is shows the ECG signals of a person, where the highlighted this highlighted red region, it denotes an anomaly because of this, because the same value is because the value is very low or like in the middle for a abnormally long time. So otherwise this value, it has already been seen by the model, but if it occurred for a very long time, then yes, it is a collective anomaly. The individual data point, they in itself might not be an anomaly in this case, but altogether it is. The second key aspect of while defining any anomaly detection problem is the availability of data labels. The labels associated with this with the data instance, they will denote if the instance is normal or if it is anomalous. So, and obtaining this kind of label data, which is accurate as well as representative of the every type of behavior a system can have, is often not possible. And that is why labeling is often done manually by a human expert who has domain expertise in that particular area, and it requires substantial effort to obtain the label training dataset. Um, but typically, getting a labeled set of anomalous data instances which cover all possible type of anomalous behavior, it is often more difficult than getting labels for normal behavior, because we see the anomalies very rarely, and that's why getting the normal data um, is often more feasible. So, like, we cannot imagine a machine which is getting getting broken down every 2 days or so. It happens only once a year or once a month or something. So getting anomalies in any system is just very rare, and that's why getting the normal data set is much more easier than relying on this kind of um, labels, basically. And due to these reasons, we basically tend to work with the anomaly detection methods, which where we do not need the labels from the data set, or at least some limited number of labels are required, which we'll see afterwards now. The first method is called supervised anomaly detection. Here we basically the technique basically assumes that the labels for the normal as well as the anomalous instances are readily available. So in this case, a typical approach will be to build a predictive model for normal versus anomaly classes, and any unseen data from the test set is compared against the model to see if which class it belongs to. So this is when this is only possible when we have the labels for both normal and anomalous classes. However, there are two major issues here. First is that the anomalous instances are way lesser than the compared to the normal instances in the training dataset, and this results in creating a biased model due to the imbalanced dataset. And the second being that the obtaining of accurate and representative labels, especially for the anomaly classes, is usually more challenging, like I mentioned before. The figure below is a representative of how the training and inference looks like in this case, in the supervised anomaly detection case. The next mode is semi-supervised, which assumes that the training data has labeled instances for only the normal class and not for the anomalous class. So since they do not require label for the anomaly classes, anomaly class, they are more popular than the previous method. We can see in the figure below how it works. So a typical approach in this case will be to create a model around the normal data set and then classify each instance from the test data to be belonging to the normal region, or if it is not belonging to the normal region. So they are they are more popular than the previous method because we don't need the actual labels of the anomalous class. So, and then there's another method which is unsupervised anomaly detection. So these techniques, they do not require any label training data, and that's why these are the most popular in the research communities at the moment, and also like in the different applications. These techniques in this category, they make an implicit assumption that the normal instances are far more frequent than the anomalies in the test data. So like we are assuming that we are seeing these kind of anomalies only once in a moon or something. So if this assumption is not correct, then definitely we'll be having more false positives or false negative alarms than the accurate predictions. The last aspect of while defining a anomaly detection problem is what is the output of the model. So some techniques basically they assign an anomaly score to each instance in the test data, and depending on the degree to which the instance is considered an anomaly. So the output of such techniques might be just a ranked list of anomalies, and at the end, an analyst may choose to either analyze the top few anomalies or use a cutoff threshold to select the list of anomalies. Some other techniques, they basically assign a label saying if the instance is normal or anomalous. So these techniques do not directly allow the analyst to make a choice of threshold levels, but this can be controlled indirectly through parameter choices within each technique. The ones which are assigning directly the labels, they also are working underneath with some kind of probability values or some score representing the level of anomality of this particular data instance. but over the hood they are just providing this one label if it is anomalous or normal. So if an analyst is able to dig deep into the model, find out where this particular thresholding is being done, he can change the thresholds, or if not change the threshold directly, he can also um, change this kind of parameters which are affecting the selection of this threshold. Now let's talk about the applications of this techniques, like of this anomaly detection problem, like where it is generally applicable. The first application can be intrusion detection, which basically means any malicious activity like break-in, penetrations, or other forms of computer abuse in a computer-related system. So these malicious activities, they are interesting from a computer security point of view, like from their perspective. Since these intrusions are different from the normal behavior of the system, they should be easily caught by the anomaly detection techniques. But it's not always the case, because sometimes these intrusions are made in a very stealthy mode, and they go undetectable by the systems. The key challenge here is the huge volume of data. Due to the huge volume, the anomaly detection technique needs to be computationally efficient to handle these large input size. So, like the anomaly detection technique, this should be very scalable with a large amount of data which is streaming in. And since it is generally these systems are working on in a streaming fashion, we require an online analysis. Like the model should be working in an online fashion. So it should not be a batch one where we are just passing the model some batch data sets and getting the predictions. Here, we generally have like small batches or like a single data points which are provided to the model, and the model basically tells if it is normal or anomalous. Due to this huge data size, it is also possible that the model is misclassifying a lot of samples. So if the false positive or false negative rate are way too high, then the analyst who is doing the manual analysis afterwards, like who is the second phase of in the second phase of screening, we end up getting a high number of data instances which are potentially anomalous or potentially normal. So the model should be very confident about the score, and it should have less false positives, or basically it should have less false alarm rates. The next application is fraud detection, which basically means the detection of criminal activities which is taking place in a commercial organization like banks or credit card companies, insurance companies, and like stock markets and so on. The fraud basically occurs when a user consumes the resources provided by the organization in an unauthorized way. So these users, they might be just the actual customers of the organization, or they might be posing as a customer belonging to that organization. And the second problem is known as identity theft. Um, these organizations basically, they are more than interested in the immediate detection of such frauds to prevent any economic losses, because it is possible that they might be losing a lot on due to these frauds, and these fraud users, they are going undetected by their current system. So we need an efficient anomaly detection system in place. The other application area is the medical health care. So anomaly detection in medical and public health, it typically works with the patient records. So since the data, it can have many anomalies due to the several reasons, like abnormal patient condition or instrumentation error. This is a very critical problem in this domain, and it requires high degree of accuracy. The data typically, it has features like the patient age, blood group, weight, etc. And in most of the cases, the aim is to detect the anomalous records which exist in the form of point anomalies. So yeah, though the main point, the main interest is in the point anomalies in this case. What we generally have is a labeled data set belonging to the healthy patients, and which the model learns on. And when it sees the data from the unhealthy person, it should be able to identify it instantly. Okay, this is an anomaly. However, the important point here is to note that the cost associated with the misclassifications, it is very high, because it is a human life at stake. So like in the example on the right, we have a brain image, and scan of a brain imaging, and the one on the left is the belonging to the normal tissues, and the one on another side, on the right side, is belonging to an unhealthy patient. And we can see that tissues, they look differently. So the models knows what a normal brain image looks like and what it is not, when it is not. The last application I'll be talking about is fault detection in industries. So in the industry, the units basically suffer damage due to continuous use and the normal wear and tear. Such damages need to be detected early to prevent further escalation and losses and the downtimes. So the data generally is recorded from the sensors mounted on top of the units, and they are collected regularly for analysis. Um, this is also a very important concept in the when we talk about Industry 4.0 or predictive maintenance. And the actions they are needed if something bad happens, the actions they are needed to be taken as soon as an anomaly has occurred. So this basically requires to work in an online setting like the one we previously discussed. So we are getting the data from the sensors. A machine which was working in the factory, its temperature is getting up and up and above a certain alarming level, and we need to take immediate action. So we should be able to detect when an anomaly is happening or it is going to occur, which is also called predictive maintenance. Let's talk about the different anomaly detection techniques. So the anomaly detection techniques, they can be broadly categorized as shown in the figure on the right. And we'll be looking more closely into the top two categories, which is like the classification-based techniques and the nearest neighbor-based techniques. The other techniques are clustering-based, statistical, information theoretic, and there are some more categories which I did not mention here. Each of these techniques, they make some unique assumption about the type of data or the type of anomaly they are going to work on, and so that these assumptions are made in order to correctly detect the anomalies. And that's why they have their own set of advantages and their own set of disadvantages when working in the actual application. Not a single anomaly detection algorithm can work in all the settings, and that's why we need different types, and we have to see the assumptions in the coming slides. The classification-based anomaly detection technique, it will learn a model or a classifier from a set of labeled training data instances, and then it will classify a test instance to be belonging to one of the classes it has learned from the model. The model has learned basically. However, the assumption here is that there exists a classifier which can be trained to differentiate between the two classes in the feature space. So like the data set that we have the labels for normal and we have the labels for anomalous instances. It should be possible that a classifier it exists which can effectively differentiate between the two labels. If it does not, then this model might not be of much use. Based on the labels which are available for the training phase, they can be either belonging to the multi-class anomaly detection technique or the one-class anomaly detection technique, which we'll see afterwards. The multi-class classification technique is here the assumption is that the training data it will contain the labeled instances from multiple normal classes. Like we see in the figure, we have more than one normal classes, so like normal class 1, 2, 3. And the anomalies which are the ones which are not belonging to either of the clusters or either of these grouped regions. So in this case, the idea is to learn a classifier which is able to distinguish between the different normal classes from the rest of the classes. So a classifier which can effectively differentiate the normal class 1 from the other two normal classes. There can be just one classifier, or there can be an ensemble of classifier, where each of the classifier is responsible for one particular class, and then we assemble the results from all these in the actual deployment. At the inference time, if like the ones which are marked as anomalies here, so if a data instance which is not belonging to any of the classes, any of the normal classes, then it will be an anomaly. In most of the cases, it is possible that these models they will be providing some kind of score, some kind of confidence or probability value, where which basically tells, okay, if this point belongs to class 1, class 2, or class 3. If the test data instance, if it is not belonging to any of these classes, or if it has very low probability to be belonging to any of these classes, then it will be an anomaly. In the second type, we have the one class techniques, where the assumption is that all the normal training instances, they belong to just one class label. So they are not multi-class, they are just one class label. So the idea is here is to learn a boundary around this normal data set from the training samples, and by we can use here some one class algorithms like one class SVMs or one and so on. When we get a test instance during the inference time, we will see if the instance it belongs inside this normal region, or if it is belonging outside the normal boundary. In this case, the anomalies which are marked here, we can see there is a circular boundary region, and the anomalies they belong outside this circular region, so they will be classified as anomalies. There are different types of algorithm which belong to the previously mentioned category. Some of these are mentioned here. We can look into them in brief. So like we have neural network based anomaly detection techniques, which will take the normal training data to learn the different normal classes, and then each test instance is provided it is provided to the neural network. And then the neural network basically, if it accepts the input, then okay, it is normal. If it does not, then it is an anomaly. Next, we have the Bayesian networks based techniques, where the idea is that the network it will estimate the posterior probability of observing a class label, and this can be done given a test data instance and the class label with the largest posterior, which it will be chosen as the predicted class. So if the predicted class is like a normal one, then it is a normal, it belongs to a normal class, or if not, then the data point will be an anomaly. The next algorithm will be the support vector machine based techniques. So what they do is they generally use one class learning techniques. They will learn a region or area around the training data sets, and when the test data set, when it arrives, it will be determined if it belongs to the learned region or not. If yes, then like we talked in the previous slide, if it belongs to this class, then good, it is normal. If it does not, then it is an anomaly. And finally, the rule-based systems, like for example, they will capture these systems or these techniques. They will capture what the decisions or what the normal instances look like. So they will capture the normal behavior of the system, and in terms of rules. And when a test instance that is not covered by any of these rules will be considered as an anomaly. One of the most common examples for the rule-based techniques could be decision trees or random forest or isolation forest in that sense. Now, this classification-based anomaly detection technique, they have some advantages, they have some disadvantages. Advantage is that we can utilize the different powerful, there are various and so many powerful algorithms at our disposal, and they can be used to achieve the great results, great accuracy, great recall, great precision, and so on. And also, since these models are already pre-trained, they will run even faster during the inference time. However, the downside is that there is a very heavy reliance on the accuracy of these labels. And it is very much possible that when we are doing the labeling manually, it is possible that the classes, the labels are misclassified, the instances are misclassified, and the model will learn it as a normal class, and which might not be the best thing to do. So this heavy reliance, they can be very harmful for the performance of the model in the longer term. The next class for this anomaly detection technique is the nearest neighbor-based anomaly detection techniques. Here, these kind of techniques, they require a distance or a similarity measure to define between the two data instances. This distance between the two data instances can be it can be computed in different ways, one of which is a classic Euclidean distance. The assumption here is that the normal data instances, they occur in dense neighborhoods, while the ones which are anomalous, they belong far away from these far away from these dense neighborhoods. So they can generally be grouped into two categories. First is the technique that use the distance of a data instance to its kth nearest neighbor as anomalous and as an anomaly score. However, the second one basically they compute the relative density in that area where they are located, and this score is used to calculate the anomaly score. We'll look at them in detail here. So like according to the first method, the anomaly score of a data instance is defined as the distance to its kth nearest neighbor in the given dataset. A different way to compute the anomaly score of a data of this data instance is to count the number of nearest neighbors in that are not more than like d distance apart from the given data instances. So we will count the number of we will define a certain distance d, let's say, and we will count the number of points that lie in that region. And that can be, so if there are not many, then it is possibly an anomaly. So this method can also be viewed as estimating the global density of the each data instances, since it involves counting the number of neighbors in a very we can say hypersphere of a given radius. The one which is on the right is the relative density, where these techniques they estimate the density of the neighborhood of each data instance. They are talking about the density, if it is a dense location or if it is not. So any instance that lies in the neighborhood with a lower density is declared to be anomalous, while the ones which lie in the dense neighborhood will be declared as normal. So the basic difference between the two is like in the first we are just counting the number of these instances which are in that region. In the second one, we are talking more about the density itself. Let's talk about the advantages and disadvantages of this technique. So the best part about this technique is that it can work in an unsupervised setting. And it does not make any assumption regarding what is the generative distribution of the data. Instead, they are purely data driven. So like we do not need labels. It is purely from the insights that we receive from the data itself. Also, adapting the nearest neighbor based technique to a different data type is very straightforward, and it primarily basically requires defining some appropriate distance measure for the given data. So for example, if you create a nearest neighbor based technique for the continuous dataset, or a dataset which contains continuous values, and if you have a new dataset where you have categorical values, now you can directly adapt the method from the first problem to the second problem by just defining some similar distance measuring score. So like in the first, if it could have been a Euclidean distance, in the second it could be just like a measure which will tell okay how the two attributes are similar or how they're very far apart. So this provides a good edge over the previous methods that we discussed about the classification based techniques. Obviously there are disadvantages also. So if for these techniques, if the data it has normal instances that do not have enough close neighbors, or if the data which are anomalous, it has so many neighbors. So like if the anomaly is rooted deep inside one of the dense regions, then it is possible that this method will not work properly. So like in cases like when the anomalies they disguise themselves as belonging to a normal class, in that case it will not be possible to identify them effectively. Next is the computational complexity that comes along with, because we are computing the distance of each instance from every other instance, and that in a very large data set this will be very computationally inefficient, because we are limited by the resources, we are limited by the time and everything. So that is another disadvantage. And lastly, the performance of this technique, it relies a lot on the distance measure, the type of distance measure that you are using. So if the distance measure can effectively distinguish between the normal and anomalous instances, good. If not, then we are in problem. So defining a good distance measure between the instances, they can be challenging when we are working with complex data sets like the graph data, or like the sequential data sets. In that case, defining these kind of distance measures is oftentimes not possible, or if possible, then it is very difficult to do so. Next, we look at one of the use cases that I worked on during my master thesis and also during my research period with Fraunhofer. The use case here shown is it is a project for an autonomous car. The idea here was to develop some and showcase that an autonomous system, it can self heal itself when a failure has occurred. And for like detecting for self healing, we first of all have to detect when something bad has occurred. So where that is the part where the anomaly detection part came up, and I was responsible for working on it. So what we have here is we have taken a race car as an example of a smart factory application which is deployed in industry. This autonomous car, it is expected to navigate from one part of the warehouse to another part and perform some tasks and achieve the certain goals. Um, so yeah, this car basically, it had a very powerful processor on top. It has a powerful battery bank. It has this ZDD stereo cameras, LiDAR sensors, and so on. It has state-of-the-art NVIDIA Jetson processors also. So yeah, it was quite powerful in that sense. On the right, we see what the overall process looked like. So we have, so the first step is to monitor the signal from the car. We have so many sensors mounted on top of this race car, like the cameras and other sensors like the IMU, the inertial measurement unit, and all, which basically will determine the speed and acceleration and all. So we have all these sensors which are mounted, and the first part is to monitor these signals and then detect the anomalies by using one of the many methods which we have seen before. Then the next step is to evaluate what was the cause behind this kind of anomaly or this kind of something going wrong. And then the system basically makes a decision on what should be done for this situation based on all the knowledge it has learned from the information presented to it during the training part. The next step is to finally take the correcting steps, execute those steps, or to fix the what has already gone wrong, or to avoid any damage which can be possible due to certain things going wrong. So all these steps, they are running in a closed loop, and until the end goal is achieved. So the end goal was, like we discussed, it has to go from one part of the warehouse to another part of the warehouse and perform certain tasks. So all these things will be going on in a loop until the final goal has been achieved. So now, just to give you some idea how complex the system might get if you keep on adding features and functionalities to such a system, here is a figure of what it actually looked like. It would actually have looked like. So there are individual components for different tasks, each generating a large amount of data which contains important information about the current state and the overall system. The race car that we had, it had more or less all of these sensors, like the odometry sensors, the central computer, the radars, the video cameras, LiDARs, and so on. And also the cameras, not just the cameras, but also LiDARs. So like at times when cameras are feasible, or like they are enough to provide us this kind of information, like what is in the nearby surroundings and all, then cameras is good. In cases when it is not possible to use cameras, for example, when a car is going against a mirror or it is going against a window, a transparent window, then a camera might not be so successful. In that case, we basically look into the LiDARs. Then they have many advantages and limitations, but that's out of the scope of this talk. Yeah, so this is a scenario under the scenario under consideration of autonomous mobile robot was that it is inside a warehouse facility, like I mentioned. So what we had is we had a hardware model of this car. It is a car which we were inspired from the MIT race car, and we created one of our own. We had also not just the hardware version, but also we had this software simulation where the car was simulated in what was the software, Gazebo. So we had simulated the environment in Gazebo. We had not only simulated the car, but also the environment around the car. So the location where you are seeing this car to be navigating right now is the office of the Fraunhofer. So it's the reception area, and we basically simulated everything, like the stairs, the mirrors, the pillars, the desk, and everything. so that when we are training it on the simulation, when we are training the car on the simulation, it is learning the exact things that it will also see in the real life scenario. So like what we did is we trained everything on the simulation, and then we transferred all the learnings to the hardware model also. So and then the hardware model was left, okay, just navigate by yourself, because it was trained on using the reinforcement learning. And just go by yourself now, because the situations or the environment you have seen during the training, it is also the same which you will see in the actual world. So it worked. These are certain signals that we used to that we recorded. So these are signal information which were generated from the sensors of the race car, and they were later recorded in a database and then filtered, pre-processed to finally provide a fairly suitable dataset for our training and evaluation purpose. The data which we recorded was for the normal operation of the race car, to evaluate the performance of the anomaly detection algorithm and the anomalies. And then like I said, like creating anomalies is very rare. So what we did is we injected some anomalies forcefully, so that they can be tested using our anomaly detection techniques. So what we did is, for example, when the car is moving, we made the friction of the tire to be infinite, so that it cannot move any further of a particular tire. So it cannot move any further, or if it will just rotate around this fixed tire or something. So so the idea was to inject these kind of forceful anomalies into the system, and we expected that, okay, when the model is deployed in the real time, they will work properly, and that yeah, so they will be able to identify these kind of anomalies and if it is happening. The time series data was recorded for components like IMU, which is the initial measurement unit. It is used to measure the linear acceleration, angular velocity, or the orientation of the vehicle. Other unit was the odometry sensors, basically, which uses the data from the motion sensors to estimate the change in position over time. And lastly, we've also recorded the steering angle, and like we were controlling this car using a joystick. So we also recorded like what was the steering and how much force was the velocity was applied to the car. So all these sensors, they provided the information which we sampled from the car, and we recorded in the database and we generated this database on our own. So these were the many algorithms that we used to evaluate the data set that we have created. These are the different algorithms we use for the anomaly detection. Yeah, so they all have their own set of advantages, disadvantages, and we wanted to see which particular detection technique it will work for our use case. It is also possible that not a single algorithm, it will be a good fit for all the situations. For example, it's possible that isolation forest, it was a good fit when we are working in the daylight conditions, and while the autoencoders, they are perfect when we are working in the night conditions. So this here the concept comes about the context, which we already discussed, like the contextual anomalies and so the context information has to be provided, and accordingly we would have selected one particular technique. We can also talk about these algorithms a bit in detail. So like isolation forest is an ensemble based method, with like ensemble of decision trees, and it is one of the most efficient methods for high dimensional data. Then we have one class support vector machine, which we have already seen. The next we had like angle based outlier detection. Here the most of the anomaly based techniques, anomaly detection techniques, they are based on evaluating some kind of Euclidean distance between in a full dimension, and they are not very effective or efficient in a very high dimensional dataset. What this method did instead was it rather considered variance between the difference vectors of a point to the neighboring data points. And if this value was very high, then it is basically a sign of abnormality. Local outlier factor is something similar to what we already seen in the nearest neighbor techniques. Yeah. So this algorithm will also compute the local density deviation of the given observation with respect to its neighbor. That's how it worked. And the next is autoencoder. So autoencoders are basically neural network based solutions, and they are one of the most simple yet efficient deep learning approaches for anomaly detection. And since the hands-on that we'll be having will be using an autoencoder, it makes sense that we look into this model in a bit more detail. Okay, so this is what an autoencoder looks like. So the autoencoders basically they are neural networks, and they are trained on to encode the input data that we provide them at the input layer to a compressed or to a compressed representation, and then it will decode this compressed representation again at the output layer. So the idea is that we provide this input data at the input layer and in the first layer, and the model will try. There are two parts. There's an encoder, there's a decoder. So the encoder model, it will try to compress all this information it has seen in the input data to this compressed representation. So for example, if the input data was it was 100 dimensional vector, then we will try to compress it to for example, 10 dimensional vector, because we know that most of the machine learning algorithms, they tend to work well with the lower dimensional. So that is also called the curse of dimensionality. So we compress from 100 to 10 dimensions. So what we are forcing is we are forcing the model to learn only the useful information, discard all the noise which comes along with the data set. So it is possible that there are certain columns from the data set which have an only constant value, or they have values which have very low variance and so like that. So we will learn only the what is most important. And then from this compressed representation, then we tell the model, okay, now recreate back the what was you have already seen. So in this manner, the model is now forced to learn only the informations which are useful, because it has to recreate it back also. So that is all the idea behind autoencoder. And now what will happen is that when we are doing this kind of compression, the ones belonging to, since we know that most of the samples are normal and only few are anomalies, so the model will be able to learn all the representation from the normal data set. And when an anomalous data set data instance it comes, it will not be recreated with much accuracy. And that's why the reconstruction error, which is like the difference between the error from the input and output layer, it will be very high, and that's why we will be able to identify the anomalies quite easily. This is how the results from the autoencoder look like. So we have the signals from the IMU linear acceleration and angular velocity, the ones at the bottom, and the red spikes are basically like the reconstruction error from the autoencoder. So the points where we are seeing these kind of spikes, these are the predicted anomalies, and the black star like objects, they are like the ground truth anomalies. So we had inserted this kind of a forceful injection of anomalies in this data set, and we had marked which points were there. And then we try to compare, okay, if the autoencoder is also providing reconstruction error at the same point or not. Yeah, so these spikes are basically like at this particular point, at this particular timestamp, the reconstruction error was very high. It means that was an anomaly, like we discussed before. Talking about the quantitative results, we use different kind of metrics like Matthews correlation coefficient, which is like a balanced measure to which like it is a measure when the class is imbalanced. So like we have more samples from normal class and only few from the anomalous class. So this is a metric which is a de facto standard when comparing these techniques against each other. Then we have other metrics like the recall, precision, and the inference time. Overall, there was no clear winner, which we could not find any single method which is winner in all the sections against all the metrics. But in the different aspects, the angle-based outlier detector, it seemed to perform the best. So because it had the highest F1 score, it had the highest MCC in any of the case. And then the inference second is basically the time it took when the input was provided and when the output was received. In that sense, like the project was quite successful in that sense, and my thesis was also based on the same. However, I did not use for my thesis the conventional machine learning models, but my focus was more on the deep learning sides of this area. So I used models ranging from vanilla autoencoders to LSTMs to Gaussian mixture models or a combination of Gaussian mixture model with the autoencoders and so on, which I can also talk about later if you want to, but I think it's good enough for the talk. These methods are good enough for the talk, I think. The next part is the hands-on, where we can actually see how the different things that we have just talked about, they come into place. I mean, this is also one of the part which is lacking from most of our curriculums. So it makes sense, like whatever theory we are learning, if we are actually able to apply it in the real world. Um, can someone confirm if you are able to see this Jupyter notebook?
Yes, sir, it's visible.
Okay, yeah, perfect. Thank you. Um, yes, so what we have is like we have I've taken this Jupyter notebook from a Kaggle note from the Kaggle website, and basically it was a good notebook which included all these graphics and everything. So you can also find all the information that we just talked about, like the PPT and also the also this notebook on this GitHub repo. So which I will leave a link at the last slide. But yeah, so let's talk about what we are seeing here. So what we're doing here is we are doing the unsupervised learning with autoencoders. The idea here is the same. Let's see in the graphics again. So for example, we are taking a sample from the MNIST dataset. So it is a numeric 4. And what we are doing is we are providing this as an input to the input layer. Now the encoder network, it will basically try to compress this complete representation into a smaller or like a lower dimensional representation, which is also called the bottleneck layer. And then the decoder network, it will try to reconstruct back the original input. And ideally, the X and X prime, they should be very identical. They should have low error, low reconstruction error for the normal samples, and it should have a very high reconstruction error for the anomalous samples. So due to this kind of bottleneck architecture, it is forced to learn this kind of condensed representation, which only contains useful information. So how we start? So like we start with importing some of the libraries. Um, so we are using libraries like Pandas, NumPy, TensorFlow. So Pandas we are using for the for like loading the data set and doing some pre-processings. NumPy, we also have some similar tasks, and TensorFlow we are using. So TensorFlow is a deep learning framework that we generally use. It is one of the most de facto standards, a framework provided by Google, and we are using it for creating our autoencoder network in this case. Then we have Matplotlib and Seaborn, which are the visualization libraries. Like we will be using it to visualize what we are already seeing in the dataset or what the anomalies have been observed. And then we are setting just some parameters. Here we have this dataset called credit card CSV file. So what the use case here is that we have some transactions from the credit card company, and we have like different these so the columns, they are basically like the time at which this transaction was done, or like there are different features which are encrypted, because so information like what was the name of the person, what was the name of the bank, what was the name of the ATM, and so on. This all information, they are encrypted, so because just to provide confidentiality of the transactions. And then we have like the amount of which the transaction was done. And then we also have this is a labeled data set where we know like, okay, if the transaction was anomalous or if it was normal. So this data set is a very common data set which you can find also on the Kaggle, or I will also upload it here on this on my GitHub repo again. So yeah, let's load the data set, and then we try to see what does the data set look like. So we have this kind of head, so like 5 samples I've printed here. So we have time column, then we have features ranging from V1 to V27. So we have like around 27 features. Then we also have the amount, which is also a feature in that sense. And then finally we have the label or the class, which is the target that we want to learn. Let's so we have just renamed the columns, and then all the columns, they have been made to shorten or like the lowercase literal, um, just so that for like visual purpose, nothing specific in this case. Then yes, then we have amount. Okay, the amount, it can be someone will be debiting an amount of 10 rupees, someone will be doing amount of 1,000 rupees. The data set in this case will be then very skewed. So we have a very large range. It has a very high variance. So what we will do is we will take a log of this amount column. What it will do is it will put it in a very uniform range. So like if it is between 10 to 100, it will put in it a range of 1 to 2 or 1 to 3. And that's why we did a log for this column. So the column here, if you can see the log 10 amount, it is we have taken the natural log of this amounts column. So now what we have is a very less skewed data set. Then what we are trying to do is we are trying to visualize these kind of clusters. Like we have two clusters here, one belonging to normal class, another belonging to the anomalous class. So what we want to do is we want to visualize it. Now we have seen already that it has 27 features plus one amount as a feature, so like 28 features. It is not possible to see these 28 features, 28 dimensional representation of the data itself. So what we will do instead is that we will try to compress these 28 features down to 2 or 3 features, and then try to plot them on a scatter plot, for example. This can be done using a tool called TSNE, which the idea is here is very simple. So it is a dimensionality reduction technique, which will map the clusters in high dimensions to a 2 or 3 dimensional plane. So we can easily visualize how we can discriminate between the different classes. And it will the principle behind is that it will try to keep the distance between the data points in the lower dimensions proportional to the probability that these points are also neighbors in the higher dimensions. So that is the idea behind the TSNE, and we'll see in working now. Before that, we already have like we have around 284,000 samples for the normal case, and very few samples for the anomalous case. This is very highly imbalanced data set. So like if I'm plotting all these 200,000 points on the plot, and only a couple of 10 data instances for the anomalous one, then we'll not be able to identify it so effectively in the visualization. So what we did is we undersampled the non-fraud class, like the normal class, and now we have the ratio which is 10:1. So for 10 samples, 10 normal samples, we have one anomalous sample. This is the undersampling which we did here in this 41 number cell. And finally we see like the ratio is now 10:1 now. So from 284,000, the number of normal samples now are only 4,000. Then we plot this kind of TSNE output. So it will look like this. We have this green class. The green points basically represent the green points will represent the normal class, while the red points, they basically belong to the anomalous class. So this is a visualization in a lower dimension. Not necessarily it will look exactly like this in the higher dimensional or the original higher dimensions, but to get some idea, it looks like this now. We can see like while the clusters for the green class and for the red class are very far apart in that sense, but there are also some anomalies. You can see like the red dots in the middle, which basically tells like some of the anomalies, they have disguised themselves to look like a normal transaction. So it will not be a very straightforward approach. So like it will not be just that we can just draw a line here, and we can just say, okay, all the samples belonging to the left, they are anomalous, and the ones on the right are normal. Because we have some points here in this cluster, in the green cluster also. So the next thing is that we do a train and test split of the data set that we had. So what we have is like we have around 284,000 normal samples, and we have around 492 anomalous sample. What we do is like then we basically do a train test split here in this 12 number cell. So like we are splitting it in train and test data sets, and also like the validation data set. And what we end up receiving is like this. So we have like the training data set of around 160,000 samples. And then we have like for the validation, we have around 40,000 samples. And the test data set is around 8,400 or something, 84,000 samples. This is the train and test split. Then we have something called normalization and standardization. So um, so normalization and standardization are basically needed. So like different columns, they have different variances, right? So one column we can see a variance between 1 to 1000 or 1 to 100,000. In the other columns we can see just the columns values ranging from, let's say, 1 to 10. In that case, what will happen is when we are doing so in the neural networks, what we generally have is a stochastic gradient approach. So these columns which have the high like they have high number of ranging, they have high ranging values, they will have a more impact on the gradient descent. So when we are like going downward in the negative gradient direction, they will have a more impact, and that's why we will try to first of all normalize and standardize this data set, so that each column will have more or less um, equal importance in this case. Um, then what we're doing is we are building out pipeline. So like we are creating a normalizer and a scaler here. So to do the normalization and the scaling of this data set, and then we'll just fit the pipeline and then see what it looked before. So earlier it looked, the distribution looked like this between the three random features. So like for v1, v2, and v3, the distribution looked like this. So we have a correlation plot here. And then for the after the normalization and standardization, it looked like this. So we can see here like it looks now more uniform and it is now more proportionally distributed. And the ranges, they are also now between only 0 to 1. So they have shrunk down. So this was the step which was obviously needed before going further for the modeling step. Now we will go further to the modeling step. This is something called, there's a tool, something called TensorBoard. So while we are doing this, all this training of the model and the inference, like we have to analyze what was the loss, what was the gain, accuracy, and all those things. We can see this in real time here. So using these kind of plots. So I had already trained the network, and we can see like the batch accuracy, it went up from 0 to 30%, and then after some more epochs, it went up till 45% or something, up to 38% or something. And the batch loss, it reduced from up here from 0.3 to down some like 0.13 now. We can also see something like this epoch accuracy. So like after how many epochs, how the basically how the um, this accuracy has improved. Let's talk about the architecture of the model. So the architecture that we have at the moment is like we have one dense layer, then we are adding some Gaussian noise, and then we are adding two more dense layers. Um, so in this case, we are encoding, we are doing this kind of modeling using the Keras library of TensorFlow. Then what we are also doing is we are adding some callbacks, which will basically three different callbacks. So like the first callback to provide early stopping. So like if a model is training and after a certain number of epochs, after a certain number of epochs, the model's performance has not improved, the accuracy has not increased, or the loss has not decreased, then we will just stop it there, because it doesn't make sense to waste our computational resources while doing this kind of training without any cause. The second is like we have added a callback to save the models, because if we found a very good model, and then we should just save the weights also somewhere, so that we can later on, we do not need to train it again. We can directly pick the trained model and perform the inference. And lastly, this third callback is for the tensor board that we saw above, like to log these visualizations in a real-time manner. Then we have, what we have is like we are training the model. So I trained the model for some 30 epochs, and after a certain epoch, so like after 21st epoch, it stopped because the accuracy or the loss, it was not improving. So we can see here the validation loss, it was 0.138 for past for 6 or 7 epochs, and that's why it makes sense to stop it just right there. Yeah. So now we'll have a look at what was the reconstruction, what it looked like. So we have already um, so the principle of autoencoder is that like we already talked about, like the normal samples, they will have a low reconstruction score, while the ones which are anomalous, they will have a high reconstruction score. So if you see here, there are two numpy arrays which are being showed here. So like um, for the at the top we have the like the mean square error for the 30 clean transactions, while at the bottom we have the mean square error for the fraudulent transactions. Now, we can see, like in case of the first one, the clean transaction, the error is somewhat in the range of 0.5 to 1 or 2 max, while in the case of mean square error, it's quite high. So it looks quite promising. Now we have to set some kind of thresholds to say, like, okay, if the reconstruction error is above a certain threshold, then it is anomalous, and otherwise it is not. So we can either go for something like a percentile based method. So let's say the top 5 percentile of the top 5% of the reconstruction error are the belonging to the anomalous class, or we can also just do it manually, like after manual supervision, or we can use some other metrics, like there's something called Z score. So the one which is used here is like a modified version of Z score itself. So it is called MAD, so mean absolute deviation, to it which will you be using to defining the this kind of threshold to differentiate the normal classes from the anomalous ones. Now, yeah. So after doing this kind of thresholding, let's look at how it looks like now. So we have these points from 0 to some 80,000 or something. The points which are belonging to the green, they are basically the clean transactions that we already know the label information about, and the red ones are the anomalous ones. Now we have drawn a yellow line here because this is the threshold that we have defined. So any reconstruction value which is which has a z value of more than 3, they have been identified as a anomaly. And if we look at it, it looks quite well because uh, maybe we can see mostly the anomalous classes, they are belonging to the upper region, which are away from the green ones. So looks like the autoencoder model worked, did its task quite promisingly. Lastly, when we see some more metrics, so like we can see here that the fraud, it was caught successfully 88% of the times. So the recall value is 88%, but we also have to look at other metrics like of this, how many were false positives, how many were false negatives. So we can see the true positive is here 79130. The true negatives is 433. The true negatives and the false positives and false negatives are there also. So there were many false positives here, because we can see here, like there are so many green samples which also belong in the upper region, which are generally classified as anomalous. Yeah. Also, since we also saw, like the autoencoder, what is it is doing, it is compressing the different the complete data set into a encoded version of it. So like reducing the dimensionality of the complete data. We had around 28 variables. Now what we do is, like, we compressed it into two. So like the autoencoder architecture that we saw at the top, what we're doing is we are compressing from 28 dimensions. We are bringing it down to only two variables. And if we can also see, like, what the distribution looked like in that latent space representation. So like we cannot obviously see what it looked like in the 28 dimensional. What we previously saw using a TSNE was using some other algorithm where they are working with the probability. And here in this case, we are using it using the autoencoder. So using the autoencoder, we can see, like in the two-dimensional, how it looked like. So this representation here, this plot here basically tells, like, the green ones were the normal ones, while the red ones were the anomalous ones. And the two clusters, they can be seen very distinctly, because the fraud ones, they are occurring in a very defined region, and they are quite separable from the normal ones. So we can have a good idea, like if the autoencoder model was allowed to train even more, or like with a better architecture, it will would have been able to make this kind of distinction even more properly. So yeah, this is the latent space representation, and this basically will be like the end of the talk. So if I just go back to this presentation, so like concluding remarks would be this anomaly detection technique. This is very important in the sense that it will help you discover so many critical ideas or the critical information from the data. And the nature of the anomaly detection technique definitely depends on the application domain. So like there's something called, we have the no free lunch algorithm theorem, where we say like not a single algorithm will be the best suited fit for every problem. So like for the different problems in the different application domains, we should be reliant on some different type of algorithm which makes assumptions which are in which are in conjunction with your problem domain also. So they have all have advantages over each other and disadvantages also. So a correct selection of a technique basically depends on what your problem is. With that concluding remark, basically I finish my talk here. I hope I'm in time, and I'd be I'd be more than delighted to have any questions.
Uh, yes, yes, ma'am. Any queries from the participant side? Any queries? Madhumita, ma'am? I don't know why is it echoing, because I'm working with a single instance is open still. It's echoing. I don't know why.
For me, it sounds clear, I think.
Okay, okay, fine, fine. Any queries from the participant side? Madhumita, ma'am, have you received any query in the WhatsApp chat box? So I think no queries are there from the participant side. However,
Mm-hmm.
it was really very informative session, Mr. Nikhil Kumar Jha, and we learned about the types of anomaly with real-time examples. The different methods were explained along with the application and key challenges. And you rightly said no free lunch for everyone, and it has also been explained with the help of your example when you explained for the autonomous car that
Yeah,
different kind of anomaly detection techniques were used there. Isolation forest, one class support vector machine. For a single problem, you used so many anomaly detection techniques, and that's really it's context specific that where to use which kind of technique. It was very
that's
clearly explained, followed by the hands-on session of autoencoder. So that was very informative, and it has definitely facilitated all the participants. And
mm-hmm.
for me, I think we can explore the different real-time use cases in which we can apply the different anomaly detection techniques. But we know it really needs a lot of practice to visualize those anomalies and then implementing all those. Thank you, sir.
Yeah.
There's really too much to learn in this area. And we can,
Thanks so much.
all the participants can reach out to you. Have already shared your GitHub repository, and definitely they can reach out to you for future learning. Thank you, sir. Thank you. It was very much informative.